بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Ready? Inshallah. Okay. So today inshallah we're going to be continuing on last lecture. So as promised, so this lecture and the previous one are both connected to each other. Whoever missed the last one is going to suffer today. Who attended last time and didn't understand anything will not suffer as much, but okay, we'll suffer a little bit. So let's start by a recap. So what we're doing right now is we're talking about the dynamics of fixed base manipulators. And what we're trying to do is trying to find a systematic approach that you can model with it any rigid body or any n-link manipulator, okay? A fixed base, of course. And we said that a fixed base manipulator will be a set of rigid bodies connected to each other by revolute joints in general. And in general, you can have 1 degree of freedom or 2 degrees of freedom or 3 degrees of freedom joint, depending on how complicated you are. The revolute joint is like a very common choice for joints, because then we use rotary electric motors to actuate these joints. So this is why it's very popular. What we discussed last time is a building block, which is the parent-child module, or this simple dynamic model. And we saw last time that it consists of 2 rigid bodies connected by 1 revolute joint in between. And this would be a basic building block that we can use and replicate and try to, in the end, describe an n-link manipulator. A recap of what we did last time on the board was that the relative pose between the child and the parent will be given by the exponential map. And you can write it in different ways. We discussed it last time. So you can have the constant transformation on the right or on the left, depending on which frame you're representing this constant twist in. This constant screw axis. The joint transformation, which is in the end, the relation between the reaction between the parent and the child on each other. So this is the reaction wrench of the child acting on the parent expressed in the parent frame. And this is the reaction wrench of the parent on the child in the child frame. And we have here the parent body twist. So the twist of the parent with respect to the stationary frame expressed in the parent's frame. So this is the parent body twist. And this is the child body twist as well. And we have here in between the actuation. So usually you're going to have here a motor that's connected, or a linear, whatever actuator that you have. And this is what will supply this the torque or the joint velocity in general. And we said that this joint transformation is in the end a matrix that's given like this. And last time we derived it and we justified it. Where does it come from? And in the end, this relates the 3 variables, which is the wrench, one of the wrenches, one of the twists, and the torque, with the angular velocity of the joint and the other wrench on the other twist in this order. This order, that the fact that we have here the body twist of the parent as an output from the parent dynamics, and the body twist of the child as an input to the child dynamics, changes the way that we describe these dynamics. So in this case, we call it an integral causality or a natural causality, in the sense that we take the wrench and then we integrate from it V dot. So we calculate V dot and then we integrate it, we get V. But in this case, we have that V is specified by V, the V of the child is specified or identified with the P, with the twist of the parent and the angular velocity of the joint. And in the end, we have that the child dynamics are an inverse causality or a differential causality. And as an output, we get from it the wrench, okay? And I think last time, these are the 2 equations in the 2 causalities. So in the first one, we have that this is the differential equation in a V, P, 0P. And then you calculate the V dot and then you integrate it, you get the V. And then this is how you solve the equation. While in the other one, you were given the V, and we need to calculate the right-hand side such that we can calculate the wrench. The V, this is a nonlinear function in the V, so given the V, I can calculate it very easily. While this one, we need to differentiate the V, and this is something we're going to look at, that actually the V dot because the V itself has a closed form solution. The V dot itself also has a closed form solution. It's a very nice way of writing the V dot. So we don't need to do any differentiation either numerically or in any other way. We can actually calculate this in a closed form solution, which is what we're going to be doing today, inshallah. Something that we didn't consider at all when we were describing this parent and child module last time was external forces. So we assume that this is just the parent connected to the child through the joint, and there are no external forces. There is no gravity, there isn't anything. But in general, you have this picture where you can also have external wrenches acting on the parent, okay, which will come from that side. And we can also have external wrenches that come on the child from that side. And you can imagine that we can use these two, the two links together with the joint in between, and then we can connect here as an external wrench to the child, another link through another joint, and so on. And this is how you can expand this to make an n-link manipulator in general. This is also how you can include gravity. So you can assume that, okay, the gravity is something at the center of mass and it's pointing downwards downwards and with respect to the Earth frame, and then depending on how you choose the stationary frame, you can represent the gravity there, and you can transform it and write the wrench in terms of gravity this way. Okay, so this is a general way of how you can also aerodynamics. If you have, for example, a drone or an omnidirectional or a fully actuated multi-rotor aerial vehicle, then you can also have the external wrenches due to the thrust, due to the propellers acting in the same, and so on. This is what we did last time for the pendulum. We said that the pendulum is a very special case. It's a trivial case, actually, of what we're describing here, where we don't have any parent. So there is no parent dynamics. And the parent velocity, as if there is some parent link, is just fixed. So the velocity of the parent is equal to 0. And then we have that this equation, the inverse dynamics of the child, in the end, just represents this one link that we have, which is just the pendulum. And in the end, we have this sequence of equation, which just comes from everything here. So everything you see in the picture here is simply these 4 equations, okay? Just written down, expanded. And it's very important. I need you to take a look at them, because we're going to expand the same set of equations, but for n links today, okay? It will look scary at the end, okay? But it's nothing else than just these 4 set of equations. The first one is the V1, which is the twist of the child with respect to the inertial frame expressed in its frame 1, so 1, 0, 1. This is the V1, 0, 1 dot. In this simple case, it's simply just given by S theta 1 double dot, because actually we have here something that was 0, but in general, you can assume that we're going to have an extra terms, actually. We're going to calculate them in a bit. This is the equation of the rigid body dynamics in the differential causality. We have that the wrench, the reaction wrench of the parent or of the fixed stationary parent acting on the child expressed in the child frame is given by this equation. We calculated the V1, we calculated the V1 dot. And the last thing is that we can relate this to the torque applied through the joint or through the actuator by this equation. Last time we showed that you can imagine that it's very simple to actually recover this equation, right? Because I have here tau 1 is equal to this. I have here the wrench given by that. I have the V given by this equation. I have the V dot given by that equation. You see, in the end, I can reduce all of these 4 equations into one, which relates tau 1 to theta double dot. And in general, it will be also relating theta and theta dot. So we're going to have in this way that the reduced dynamics will be a differential equation between the taus and the theta dots and the theta dot, the thetas, the theta dots, and the theta double dots. Okay, which is the reduced case. For a simple pendulum, we just have this equation. We showed last time that the m is given by this term. If you put the inertias in the way that we did last time, and you have the screws in the way that we defined last time, you get the standard equation, which was, I think, some inertia around the z plus ml/2 all squared and so on. Okay, which is the standard equation for a pendulum. You should know how to derive it. Any questions from last time before we start with the new stuff? Okay, so you understood everything. Very good. Okay, so the analytic expression of the VC with respect to 0 in the C frame, but the dot, okay? Because we need it in general. You see, if we go back here, in general, we need to calculate it not just for the simple pendulum case, we need to have it in a more general form. So we will calculate here in a more general form. Recall that this is how we defined or how we identified or how we calculated the C with respect to the twist of C with respect to 0 expressed in C. We wrote it as P with respect to 0 in the C plus C with respect to P. Okay? And you see here, this P and that P, they cancel out. Okay, and everything is expressed in the C frame, so this is a correct equation. This term is given by that, and this relative twist is given by the joint velocity. Okay? Make sense? Let's differentiate that equation and see whether we can do it or not. We have here, this one differentiated will give us this term, so that's easy. This term differentiated will give us two terms because we have here, we have a dependency on time in terms of the angle, and we have here another dependency on time in terms of the parent twist. Differentiating, taking this one, multiplying by differentiation by of that gives us this expression, okay? But this one, we need to look at it more closely. You know how to calculate the differential, the rate of change of that joint, right? What does it equal to? That joint again multiplied by the smaller joint. Clear? There was a relation that related the adjoint multiplied by two big so the small adjoint multiplied by two big adjoints from the right and the left. You remember it was in the assignment, and it was equal to the adjoint but expressed in another frame. You remember that? If you use it here, you can write again this same expression. I can use it, and this is part of the homework, so you're going to take your time to try to work it out. I can write this term, okay? Only the green one. These two ones will be the same in all of the three expressions, but this one I can write it differently depending on which identity I use because I have these different identities. I can write it either as this term or that term or that term. Okay. The first one, you see it's an expression that takes the V of the child with respect to 0 expressed in the child, which I already calculated. You see, I already have an expression for it. So I can calculate this term. And it's written here in terms of the unit screw, sorry, the screw of the joint and the joint angle. So this is something that we already have all of this information coming from outside. I can also, the adjoint has a very nice property that if you have you remember last time when we said that the adjoint of some twist with respect to itself is equal to 0. No, it was equal to 0. If you have the adjoint of V1 with respect to V2, and you swap the order of 1 and 2, what happens? You get a minus sign, okay? Because this is just a property of the adjoint. It's actually a general property because this is more, this is just one way of how we're writing what's known as a Lie bracket. So if you ever heard the term Lie bracket, this is something related to it. So when we swap these two together, we get a minus sign from outside. So this is just what happened. What you see also this one, which is the C with respect to 0 expressed in C, I can write it as the sum of these two terms, right? So C with respect to 0 expressed in C is given by the sum of these two terms. I have this one and that one. The adjoint is a linear map. So when I take the adjoint of the sum of these two is equal to the adjoint of the first one plus the adjoint of the second one, okay? Only the adjoint of the second one, which is this term, is the one that remains, while the adjoint of that one, this one with respect to this one, is equal to 0. Can anyone see why? Why? Why is the adjoint of the CPC multiplied by theta dot, multiply, and you take the adjoint of this term, you get 0. Why is that? What? Because it's the same twist, right? In the end, it's the same twist. So actually, this term is VCPC, and this term is also VCPC. So in the end, they just cancel out. Okay? So this is why we get this term in the end. Okay? So in the end, these are just all three expressions. They are all equivalent to each other by just some identities. So there's nothing fancy here. You're going to work out the details, inshallah, in the homework, and you're going to see, in fact, that they are really identical to each other. Okay? It's just that the last one is very convenient for what we need today. That's why I just did all of these calculations so that we can see this last one because we're going to be needing later. Okay. So this is just very quickly the analytical expression of V, the twist, the rate of change of the twist of the child with respect to the 0 frame expressed in the child frame. Now let's look at the two-link manipulator. Okay. Again, the two-link manipulator is just a special, again, it's the next It's the simplest manipulator, and the next more difficult one compared to just the pendulum. Okay, it's just two links connected to each other like that. It's just a replication of what we had. So this part alone was the pendulum, and then at the last part we just add another joint, another motor, and another link. We just make this two-link pendulum, so the two-link manipulator, which in the end is just a double pendulum. And this is, again, you see, nothing is new here. We were just replicating, copy-pasting what we discussed in terms of the equations. So the equations are just expanded. We just have more terms and so on, but in the end, they are the same set of equations. And this is, how do we calculate now in the same way that we did? How can we calculate the taus, tau 2 and tau 1, as a function of theta 2 dot, theta 1 dot, and theta 1 and theta 2 and theta 1 double dot and theta 2 double dot. So this is the goal of what we're trying to do. And you can do it in this order, okay? So this is the general procedure, how you can actually do it in a recursive way, and this is known as the Newton-Euler inverse dynamics algorithm, okay? It's just a recursive algorithm that will start from the 0, okay, which is this side, and it will follow all of the brackets, all of the arrows that go to inside, and then in the end, it will calculate everything that's going outside. It's very simple. From a computational point of view, it's a very simple algorithm, okay? Let me show it to you first graphically here. You see we have here we have a 0 twist. What is that twist? Just the parent, which is the fixed, right? So we have a fixed base manipulator, so the base is fixed, so its twist is 0, right? So this is the parent. And then we have here theta 1 dot. You can calculate here its relation to V1, right? And then V1 would go into the child inverse dynamics. And then I can calculate with it, again, I already calculated with V1, but it goes into another joint with theta 2 dot. And then I get out of it V2. And then it goes into the child inverse dynamics. And as an output, we get the wrench of 1 acting on 2, the reaction wrench. And then it goes into the joint, I get this one. And then it goes into the child inverse dynamics, I get that one. And then it goes into the joint, I get this one. You see? So this is how the equation works. Okay. This is precisely what we had. Go back to the pendulum equation. This is precisely this. So you see that tau as an output is equal to this as an input. And this as an output is equal to these two as an input. And I have these two calculated from the theta 1 dot and the theta 1 double dot. Exactly the same, just expanded with n links. In this case, 2 links. So in the forward iterations, these are all of the expressions we are using. We just have I and I minus 1. So I here goes from 1 to 2. So the h of 1 with respect to 0, okay, is what goes, for example, is what's used here in this this joint expression, is given by the exponential map. The twist of 1 with respect to 0 expressed in 1 is given by everything else we had. We just have here 0 with respect to 0 expressed in 0. What is this term? 0, right? So the twist of the 0 frame with respect to the 0 frame is equal to 0. It's not moved. So this expression just pops out, and we have this term. This is precisely what we have for the pendulum. But in general, not. You see, when we calculate, for example, V1 with respect to 0 expressed in 1, you're going to have, V2 with respect to 0 expressed in 2, you're going to have here another term that depends on V1 with respect to 0 expressed in 1, and so on and so forth. So this is why it's a recursive algorithm. And the V dot is given by this expression we just calculated. Again, the V1, 0, 1 dot, and the V2, 0, 2 dot, again, we can calculate them recursively. So this is the forward part, going from all of the inputs going up to from the 0 frame to the 2 frame. And then we can go back from the 2 to the 0 frame with these two expressions. So we have that the wrench, again, acting on the 2 frame by the 1 frame is given by this equation. What we have here as an extra term, what we have here as an extra term is the external wrench that acts on the child. You see, this child, it can have an external wrench. In this case, it doesn't have anything. So when we're calculating W1, 2, 2, in this expression, we're not gonna have anything here. But when we calculate this expression, W0, 1, 1, we're gonna have a term that comes from this one as an external wrench. Okay, so this is, again, we just use it recursive. In the end, in the same way that you need to believe me, at least for now, that we can reduce all of these expressions to get an equation that looks like this. Okay? Tau 1 and tau 2, again, stacked together, will be some matrix. What will be the dimension of this matrix? 2 by 2, right? So I have here theta 1 dot and theta 2 double dot. This is a 2 by 2 matrix. Will give us in the end tau 1 and tau 2. And I also have an extra term here, which is what is the dimension of this matrix? 2 by 2 again, which is, okay, will be multiplied by theta 1 dot and theta 2 dot. And in the end, we have some terms. This is exactly what we had in the pendulum, but all of this, we had only theta 1, not theta 1 and theta 2. This term was 0. We showed it last time, if you remember. We showed that this term was actually 0. We didn't have any terms here. And the m was not dependent, was only one number, was a scalar, was a 1 by 1, and it was not dependent on theta. That's why it was just a constant. And we had tau 1 equal to m multiplied by theta dot. In general, okay, you can do the same procedure if you have an n-link manipulator. N can be 100. Again, this is where you use the computer to calculate all of this. And M will be an n by n matrix, C will be an n by n matrix, and so on. And you're going to have here n torques, because you're activating n torques, and you have here n theta dots, and n theta double dots and n theta dots. This will be the equation of motion for a manipulator, the reduced equation of motion. And this is what you put on the computer and you simulate and so on and so forth. Okay. Now let's derive. Okay, so now this is just the general equations. Let's write on the board what is the m given all of these equations that we already started with, which is what you already are familiar with from the child inverse dynamics and the joint transformation. Let's try to compute what the m will be and what this C matrix will be. Mubarak, other questions? Not yet. Yeah, we're just going to remove them from the game for now. It's called the reduced. Okay, even if we have the gravity, it will be still called the reduced dynamics. Okay, why we call it a reduced dynamics is because okay, let's see how to see it easily. So this equation, this dynamics that we had, you can also still simulate it on the computer, right? So there is nothing wrong with it, but you need to simulate it in what's known as a differential algebraic solver, because this is not an ordinary differential equation. This is what's known as a differential algebraic equation, because you have a bunch of equations that are differential and a bunch of equations that are algebraic, and they are constraining these equations, right? Because this is what the joint does, remember? It constrains the relative motion between these two bodies to be 1 degree of freedom, and this one to be 1 degree of freedom, and so on. But in the end, how many degrees of freedom does this system have? Let's do the calculation of last time, if you remember. We have here 6 degrees of freedom and one joint, 6 degrees of freedom and one joint. So this, how many total degrees of freedom? I have 12, and then I have this one reduces 5, and this joint reduces 5. So in total, how many degrees of freedom? In fact, even if I simulate here a 12 by 12 differential algebraic system with 10 constraints, what is actually moving or what's actually changing is a 2 by 2 system or a 2-dimensional system. You see, this is why this is known as the reduced dynamics, because we just reduce it in the directions of motions that are in the end allowable, which is motion around this axis and motion around this axis. Everything else is constrained. That's the idea. Yeah, yeah. Stability is something that we haven't talked about. Next time, inshallah. Again, we haven't talked about what stability is, so I cannot answer that question. Okay, you need to be patient. Okay. Any other questions? Okay. Then let's keep it after the lecture. Okay, because we really have a lot to do. Okay, and I'm pretty sure you don't want to stay till suhoor. Okay, so let's go to the board now. Okay, so let's see. This one. Okay. Let me just draw the pendulum again for reference. I have this. I have here the center of mass. So this is the 2 frame, this is the 1 frame, and this is the 0 frame. we have here S1 0 theta 1 dot. We have S2 1 theta 2 dot. Just as a quick exercise, can someone tell us very quickly what these two twists will be? So these are 6 numbers and these are 6 numbers, right? 0 0 1. The distance here, that each link has a distance of Li. So I have a distance, this one is L1 and this one is a distance of L2. So this one will be 0, L over 2, L1 over 2, 0. This will be 0, 0, 1, 0, L2 over 2, 0. Okay. So this twist seen from this frame is minus L over 2, L2 over 2 in the X direction. So it's a minus L2, but you remember how do we calculate this term? By taking the cross product with that one, okay? With some minus sign, okay? So this is how we get this. And this is just as a test, you can do it, you can check it for yourself. The forward iterations. So what I'm gonna do now is rewrite the equation that we had in terms of I and I minus 1 and everything just in terms of 0, 1, and 2. That's it. Okay, so we're just gonna expand the 5 equation that we had into 10 equations. That's it. Question? No, because this is 2 with respect to 1 expressed in 2. This is different from what we did in the first lecture when we talked about the product of exponential of everything with respect to 0. Okay. So the first set of equations is that we have h1 with respect to 0 as a function of theta 1 is equal to h1 0 in the 0 in the home position multiplied by e till s tilde 1 0 1 theta 1. And then we have that h2 1 of theta 2 is equal to 2 1 0 e s tilde 2 2 1 theta 2. Okay. I'm just rewriting the same equations in terms of 1 and 2, just so that you see them for once at least in your life, all in one in front of you. We're going to do some manipulation, and so from now on, this will be something you can easily program in the computer. Okay. In the second set of equations, we had that v1 0 is equal to s. We had here, you go back to the equations, if you wrote them down, you're going to find that we had here a 0 term, okay, because it's related to the parent. And then we had here S1 1 0 theta 1 dot. Then we have V2 2 0 is equal to the joint 1 2 theta 2 V1 1 0 plus S2 2 1 theta 2 dot. Make sense? Easy? Okay. The third equation is differentiation of that. You don't need to redo the differentiation. We already did it in a very general form. Okay, we just plug in the indices. So we're going to have that V1 1 0 dot. Just because of the simple expression we have, we also have a 0 here plus S1 0 theta 1 double dot. Then we have that V2 0 dot is equal to let's see, we had an add 1 2 theta 2 V 1 0 dot minus. This is the term that we just calculated, which is okay. Then we have one last expression, which is the 2 2 1 theta 2 double dot. Do these equations make sense? Okay. Any questions? Easy. So these are the forward iteration. Right? In the backward iteration, we're going to calculate the wrenches and the torque, right? So everything here is, you can think about, this is just the poses, the homogeneous transformations. This is the the velocities, and this is the acceleration, right? So position, velocity, acceleration. What we're going to be calculating now is the relation between the wrenches, which is the co-vector equation, right? The wrenches and the momentums and everything, and the torques, okay? So the backward iteration, we're going to have the wrench of 0 acting on 1 expressed in 1 is equal to, just given by the inverse dynamic equation of the rigid body. You see, this was the dynamic equation, the inverse dynamic equation of the link 1, which was the link in between, right? It was between the fixed parent frame, which is the 0, and between the two frame, and sorry, the two link. So you can imagine that it has some, so this is the inertia of the first link itself. This is the gyroscopic and Coriolis terms of the first term itself. And this is the wrench, the reaction wrench that comes from the 0 frame. And you can, sorry, the 0 link, which is the base. And you can imagine that this is the reaction wrench that comes from the external wrench, from the 2 link. Okay, so this is the reaction from the 2 link. So 1 is in between 0 and 2. So this is the reaction from the 2 link, and this is the reaction from the 0 link. Okay, and we're calculating here. This is for the link 1. Questions? Okay. When we do the same for the 2 link, so the 2 link is connected to the 1 link, but not with anything else. So there's nothing else after it. So because it's the leaf of the tree, right? So we have here, this is I2 to V2 dot minus the joint transpose of 2 to 0, I to V to 0. And there's nothing else. Let's imagine, just for a second, that the 2-link manipulator is pushing on something, because this is a robot, right? So it's going to be pushing on a wall. It's going to be drawing something. It has a tool that's, I don't know, doing something with it. What else? Then the tip of the robot was what we call what? The end effector. So you have also a wrench that's on the end effector, right? So you're going to have here an extra term that's on the end effect, right? So this is what we discussed, that you can always add external wrenches in this way, okay? We're not going to be doing it for now, so we just assume that the robot doesn't interact with anything. There's no gravity also. We didn't talk about gravity, so we don't have any extra terms. Have a question?
Here, we are getting the force by wrench by second link reaction on the first link.
Let's see. This is the equation for the first link, right? So you want to see the reaction of what is the external wrench that you have on the first link? You have a wrench that comes from the 0 link and a reaction that comes from the 2 link, right? So this expression should be equal to minus the reaction wrench from 2 on 1 expressed in 1, right? Or the adjoint of 2 of this expression, but expressed in 2, and I transform by this. And then if I swap the 1 and the 2, this becomes a plus, and this becomes a 1, and this becomes a 2, right? Because the reaction of 1 on 2 is the same as the reaction of 2 on 1, but in opposite direction and the same magnitude, right? Newton's third law, which is how we end up in this equation, okay? And this is, if you remember, that this minus adjoint transpose was part of what's in the joint transformation. If you go back to the equation of the joint transformation, there was a point that related to the reaction torques in each other. And here I just used it in this expression. So this is the fourth set of equations. The last one is that we have that tau 1 is equal to S1 0 transpose 0 1 1, and tau 2 transpose by. You see everything we're just replicating. Everything, we haven't said anything new so far. I wrote all of the equations that you know. I wrote them with I and I minus 1 in general. I wrote them with 1 and 2 and 0 and so on. So we're just playing around games, okay, so far. But now to calculate the reduced dynamics, we would start again from these equations. Again, you would start from tau 1 and tau 2, plug in the wrenches from these two equations, take the v dot and v dot from the two previous slides, the v and the v from the previous slides, and so on and so forth. You see now that we will start to have some coupling, right? Because when we're calculating the 1 and 2, we're calculating the 0 and the 1, which is the one in between, we start to get some expressions. Yeah, this one, you see, it's replicated here, you see? So this one is also here. So and then I start to get some relations and some coupling between the v dot and the v dot in the same equation, and so on and so forth. Of course, doing it in the same way that we did last time by just plugging in the equations will be a tedious job. Let's try to do it by matrix manipulation. We're just gonna pump in all of these expressions, put them in a very big matrix form, an unconventional one, and just solve this in this system of equations, and we'll see whether it has a closed form solution or not. Okay? So this is what we're gonna be doing. This part is a little bit scary, so I end up just as for your convenience. These two set of equations, we denote them by equations B. These two, we denote them by equations C. And these two are equations D, and these one are equations E, okay? So the E are for the torques, the D's are for the wrenches, C's are for the V dots, and B's are for the V, okay? The twists. Let's write the exact same equations in matrix form. We're just gonna pump them all together. We're gonna take the V's together and write them like that. Anything with a dot means what? 0, okay? Okay. So the first, if you wrote down the equations, these are the first two equations, okay? Just written in compact form. So nothing new again. C equations were in terms of V dot. So I have this exact same equations, you see? The exact same matrix. I have it again. And now this is also multiplied by the V dot. We had another term that was like that, but multiplied by the theta double dots. And then we had the expression, which is the new one that we calculated. Remember that came from the time differentiation of the big adjoint, and we had the adjoint and what I showed you earlier. So we had, again, we can write it like this. Okay. So we have the same expression here multiplied by the dots. So you see V dot is equal to something multiplied by V dot. So it's an equation in itself. This is why we have the coupling. We have the S multiplied by the double dots. Here we had the S multiplied by the dots. And then we had this extra term which had the small adjoint. It had here something with the big adjoint, and it has here the V1 and the V2. Okay? And this, you see, this expression is exactly the same as what? At these two, right? See, we're getting a replication of all of these. Okay. Then we have in the D expressions, we had the wrenches, is equal to the inertias. We're going to combine them into a huge matrix. Remember, the inertia itself, each one of these was a 6x6 matrix. So we're going to combine them together. We have the V dots. We had the expression that was for the Coriolis terms and the gyroscopic terms. Each one of these expressions was transposed, remember? So we had here the add transpose, and we had here the add transpose. If we combine them together in one matrix and we transpose it, we get the same terms again, right? And then we have here the inertias again. And then the wrench equations, one of them had a coupling because the one link was in between the 0 and the 2, so it had some expression, had some relation from the other one, and we have this term here. And the last set of equations is that torques is tau 1, tau 2 is equal to Does this make sense? Intuitively, at least, and not with the details. Yes. All of them from C. All of the or only C1. Okay, let's go back. What about this term? Does this make sense? This C term make sense? So V dot, V1 dot was equal to that term, which was the differentiation of this expression. And the V2 dot is the differentiation of that expression, right? So you remember when we differentiated this one, we got two terms, this one and that one. We differentiated that one, we got this term, right? Okay. We just took this expression, these two equations, we wrote them in a matrix form, you see? So I have here S1, S100, S1101, theta double dot, S212, theta double dot, right? I combine them into, where is it? This one. And this one, okay, is zeros in the first row, so which means that V dot has nothing to do with V dot, and V1 dot has nothing to do with V1 dot and V2 dot. But V2 dot is related to V1 dot by some adjoint, right? This is this expression that we had here. V2 dot was related to V1 dot by some adjoint, you see? And the last one is that we had an adjoint, a small adjoint, with the big adjoint with the V1. So you see V2 dot, I have an expression that couples it with V1 dot. So with V1 only, not V1 dot. Which is, you see this line and this expression, you see? It's this one multiplied by that one. There are a lot of zeros here, right? So first of all, these two rows are 0. So 0 multiplied by, so row multiplied by column, I get here zeros. And then I want to multiply these two, this row by this column, which will have, this row by the 0 on top, and this 0 by the one on the bottom, I get 0. So you see, the first expression is nothing, it doesn't change, right? We expand it in this way so that we can write it in a closed form solution. So we added some terms that are actually 0. This is what we did here. So we just added some terms that, so for example, this one, we didn't see it at all. We just added here to have this nice matrix that looks like that. Okay? Yes? The V dot? I'm just rewriting the same equations. Nothing new. the small adjoint, this one. So you see, this expression is the product of three terms: the small adjoint, the big adjoint, and the V1, which comes from small adjoint, big adjoint, V1, in this order. So this is a 2 by 2. Again, not a 2 by 2, but I mean a block diagonal 2 by 2 matrix. These are blocks. So again, you multiply it in the same way that you do with the rows and columns, right? So rows multiplied by columns, but again, blocks here. So this block multiplied by that block plus this block multiplied by that block, you get 0. This block multiplied by that block plus this block multiplied by that block. So in the end, I just have here one block of zeros, and the other block, and the one in down, is add h multiplied by v1. And then take this two blocks on the top, one on the top and one on the bottom now, multiply by this diagonal block matrix, right? So this one on the top, which is 0, get 0. The one on the bottom, you get this one multiplied the one on the bottom, which in the end you see, we recovered the small adjoint, big adjoint multiplied by v1.
But here, we're expressing it in S and theta dot. But when we're writing the range equations, we're expressing it in terms of V. So is there a difference, or it's just a choice?
No, that's just a choice. No, that's just a choice. It's the same thing exactly. Yeah, that's right. Actually, while I was calculating this, I'm just following what's in the book. I'm pretty sure you can write it in many different ways. Okay, but nothing will change. Actually, these two terms, maybe if you wait till the end, you're gonna see. Actually, in the end, we're gonna combine them in the C matrix. So it doesn't matter whether you write it in this one or that one. It doesn't matter. Just your computer implementation. Okay. So these are the big matrices. Now let's just introduce, I'm gonna rewrite again these matrices in a much more compact form before solving them, okay? You see now, there are a lot of, there's coupling between these equations. So you can imagine that we can actually reduce them together, right? I'm gonna introduce some intermediate matrices so that these are new matrices, will not have any indices. Just to what's in front of you here, I'm gonna call them new symbols. So I'm gonna call this one capital V. Make sense? And this one V dot. And this one capital range. Right. And this one just tau. Okay. So this is V equal to something in V. This one, what do you call it? Capital S. What this one? Theta dot. You see what we're doing? Just giving new symbols to these things. We're just defining them. We're going to call this one A, capital A, as a function of theta. In general, this one is a function here of theta 2 in this case. But in general, you're going to find that this is a function of theta 2 and theta 3 and theta 4 and theta up to theta n when we have an n-link manipulator. So I'm going to write it as a function of theta here. This one is the same one on top, so it's A of theta. This is, I'm not going to repeat the one that are, let me just remove that. I'm only going to introduce the new ones. I'm not going to write them again. So let's remove also this one so that we define them once. So I defined here the V dot, the W, and the tau, A of theta, S, and the theta dot. This is, I'm going to call it theta double dot. I'm going to call this guy big AD that eats S and theta dot. Again, this is just a name. It's not an operation that eats anything, right? Because this, I'm not eating this matrix and this vector and so on, right? It's just what we call this expression, we call it add S theta dot. This is we had before, this we had before. This one, does anyone recognize that one? It's the transpose of A of theta, exactly. What about this one? Capital I, inertia. What about this one? The transpose of add of V. Where is the transpose of it? Yeah, that's the transpose of that, exactly. And S transpose. You see what we did? Took the same equations, wrote them, introduced some new variables. Now let's write these 1, 2, 3, 4 set of equations into these compact forms and see what do we get. So the compact equations in the end can be written as follows. V is equal to Easy? Nothing else. Right? Same equations. Again, I expanded them. I'm just expanding and contracting everything. I'm gonna rewrite the same equations in a form so that we can solve them. This is the last time we'll do, okay? One before, so that I'm 100% honest. So the one before. So you see, this is an expression in terms of V, right? So I can bring this on the other side. What about this one? I can bring the V dot on the other side. What about the wrench here, you see? I can bring also on the other side. That's exactly what we're gonna do. So I'm gonna introduce this matrix, which, let's call it identity minus A of theta. You see, identity minus A of theta. Again, this identity is an identity matrix that has the same dimension as the A of theta, right? Because here I have V minus this expression, and I take the V as a common, right? So this is equal to S theta dot. I have the same matrix, this huge matrix, multiplied by V dot equal to S theta double dot. Are you comfortable with this term? You see here, how did we go from here to here? So we had here a wrench, and we had A transpose. I put it on the other side, and if you have A plus B, and you transpose both of them, then it's equivalent to the A transpose plus the B transpose. And the A transpose here is the identity, so the transpose of the identity is the identity. So we get this term, okay? So this is exactly the same. Okay? And then I have the last one is tau equal to, okay. Now the question is this matrix invertible, right? The last thing we want to do is that we want to write this as V equal to something, right? So we want to invert this matrix. Is it invertible? Luckily, yes, it is invertible. The A of theta, this special structure that it had, this one, is what's known as a nilpotent matrix, if you ever heard about it. It's a nilpotent matrix of order n. Because when you, and here in this example is 2, because we had a 2-link manipulator, right? If you take the A squared, if you calculate the A squared, what do you get? Right? So if you multiply this by itself, right? So rows by columns, I get 0. 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 So you see, A squared will be 0. If you have a 3-link manipulator, this will be a 3 nilpotent matrix. When you multiply A by A by A, you get 0, and so on and so forth. So this is a very special structure. And this very special structure, luckily, has a very nice closed form solution. It looks like this. So the inverse of this expression, okay, we're going to be calling it L of theta. And in this example, only in this 2D example, it will have this expression. It will have something like this. It's I0, I add H1 to of theta 2. And so this is only in this 2-link example. In a 3D case, you're going to get extra terms with the add of H12 and H23 and H31 and so on and so forth. Okay, so it will always have this nice structure. So the expression on the top, in the end, we can write it as that V is equal to L of theta S theta dot. V dot is equal to L of theta S theta double dot minus L of theta add S theta dot A of theta. V L transpose theta inertia add transpose V I V. Then we have that tau is equal to S transpose. Okay. This is precisely what we had for the 1-link manipulator. If you remember, we had 4 equations. V dot W and tau. Here, of course, it's huge, scary, but it's the same idea. So tau is equal to something multiplied by the W. W is something in terms of V dot and V. V dot is something in terms of theta double dot, theta dot, and theta and V. And the V is equal to something in theta dot. So what can we do with these four equations? We can reduce them into something that's in terms of tau, theta, theta dot, and theta double dot only. So we can eliminate the V dot, and the W by combining all of these four equations into one. Okay. Exactly what we did for the one scalar case last time. Again, just need a couple of days to work this out yourself. So in the end, you get this expression. Where is it? Okay. Get that tau is equal to this is the four equations into one. Yeah? It's a nice homework exercise in the weekend, inshallah. Okay. These are just the four equations into one, nothing else. When we had the 1D manipulator, which is the simple pendulum that we had, all of these terms were zero. And these 1, 2, 3, 4, 5 expressions were combined into one. We called it M, right? We just had M here. So this is what the tau equal to M theta double dot that we had for the simple manipulator. In general, we have extra terms, of course. And it makes sense. If you have one pendulum, it's just one rigid body that's floating. It's just no dynamics. But when you have extra, if you have N links, all of them affect each other by something that looks like that. We're just going to combine all of this to, and that's the end. We're going to call everything here M of theta. Everything here C of theta only, and theta dot. You see, this is why we have here the theta dot. You see, it's a function of the theta, where in the L and in the A, we have the theta. But in the add, where we had the S dot, okay, so the S multiplied by theta dot, this is also a function general of the theta dots. Okay, so in the end, this is an equation, looks like this. Tau is equal to M of theta multiplied by theta double dot plus C of theta, theta dot, multiplied by theta dot. We could have, and you're going to find that there's a lot of ways of writing this in the literature. You can say that this is C of theta, theta dot, multiplied by theta dot, or you can take all of this expression and call it C of theta and theta dot. You're going to find both in the literature. Don't get confused, okay? The reason why this is popular, because this is a matrix, and this matrix itself, you can write it again as something multiplied by theta dot, and you get what's known as the Christopher symbols. We're not going to be doing that. If you ever took a course on robotics, this is where the Christopher symbols come into place, if you ever understood it in any place, okay? But if not, you can look at it. If you look at what the Christopher symbols are, they are one way of writing the C. And again, we don't have time to go into it, but they have a very deep geometric meaning related to the manifold and blah, blah, blah. No time to go into it, okay? That's another course. And that's it. Now let's look at the dimensions to make sure that we're doing everything right, okay? We need to check here. Let's do a sanity check, whether the dimensions are correct. Let's just say what the dimensions of the V dot are. Remember, if you go back here, this one. What is the dimension of V in general? Not just for the two-link manipulator, in general. It's 6n by 1. 6 multiplied by n by 1. In this example, I have 6 by 1, and below it I have 6 by 1, which means it's 12 by 1. If I have an n-link manipulator, then I have 6n times multiplied by 1. So I have 6n times 1. The V dot is the same. So in general, these two, they live in 6n by 1. Clear? What about the range? Of course, it's the same. It's just for notational purposes. Remember what we called it? We just called it a dual. Why did we do that? To emphasize it is a covector, not a covector. And of course, you see it clearly here. You see how the wrench equation gets L transpose. And the L here is definitely not an orthogonal matrix, right? Remember when we discussed that vectors and covectors they're going to be transforming the same if you have an orthogonal basis, right? This is not the case here. So this is similar to what we had, the adjoint but expanded version of. Okay, so we just write it like this. It's again a 12 by 1 vector. We write it as 12 by 1 numbers, but we say it's a different space so that we emphasize it changes coordinate differently. What about the S? Let's go here. This one. Think about it first. Each S, one of these, was what?
6 by 6. 6 by 1.
6 by 1. If you go back here, where was it? You see this expression? This was 6 by 1. This was 1 by 1. So this is 6 by 1, right? This is just the unit axis, the one that we calculated here. See, don't get fooled by we wrote it here by 1 by 6. Remember what we discussed before. This is just one way of writing it. It's in the end 6 numbers together. You write it as a row vector, as a column vector, it doesn't matter. It doesn't change anything. Okay, it's just how you put n numbers together. So here I wrote it like this just for space purposes. Okay, but in general, it is a 6 by 1. It has the same dimension as the V, 6 by 1 vector. So now when I combine 6 by 1, and then I have another 6 by 1, what is the dimension of the S? 12 by 2, exactly. In this example, it's 12 by 2. In general, it will be 6n by n. 6n by n, exactly. In this case, it was 12 by 2. In general, it will be 6n by n. What about the last ones, which is the inertia? The tau is the same. Okay, that's a good point. Let's do the tau. So the theta dot, what's the dimension of it? In this example, theta dot was 2. In general, it will be n. The tau will be also n, but let's write it n dual so that we emphasize it changes coordinate, just as an emphasis. The last matrices are the inertia, the A, the L, and the add that eats anything, right? So here I say an add that eats star because we used this several times. You see, we had here the add, actually the add here that ate an S theta dot, and we had here an add that ate an L S theta dot, right? So just in general, we're going to call it add star. Where do these matrices live? 6 by 6, no. 6n by 6n, yes. You can check it for yourself. 6n by 6n. Okay. Which in this case is a 12 by 12 matrix. Let's do a sanity check to see whether you know matrix multiplications, right? Everything needs to work out in the end. Let's see whether these numbers make out in the end here make sense. Let's see the m. What about the m? What's the dimension of the m? So this one is an n by n, and this one is an n by n. So let's see whether in the end we actually get by n here. Let's start from the right. So S was 6n by 6n multiplied from the left by 6n by 6n. So 6n by 6n, 6n by 6n, 6n by 6n gives you a 6n by 6n in the end. The 6n by 6n in the middle multiplied by 6n by n gives you a 6n by n multiplied by an n times 6n gives you an n by n. So this makes sense. You can do the same here for this one and check for yourself. So in the end, everything will work out. Just as one thing very powerful here, and you can see it clearly from this expression. Even when we had something that's complicated, we have many rigid bodies together. You see the inertia, this generalized inertia. How does it change coordinates? With some matrix, and it's transposed here. You see it? You remember what we said about the inertia? It always is a 0 to tensor, right? So a 0 to tensor always changes coordinate like this. A and A transpose. The vector changes coordinate by the L and the S, while the covector changes coordinate by the L transpose and the S transpose, and so on. You see, it's all encoded. If you don't see it, this is just a remark. Maybe it makes sense at some point, but if not, this is what you need to know. That's it. Okay. the last part about the transformations. So in the end, we say this is a mass matrix. And this was inertia. What was the inertia? It had mass and moment of inertia and so on, you see? So the M here is nothing else than the I, but change with the change of coordinates. You see? L, if you go back to the L, it had some adjoints in it with some extra stuff, just because we have multiple rigid bodies. And if you go to the S, there was nothing else than unit twists. So it was a bunch of twists together. So this change of coordinates. Okay. So in the end, you see we have here a transformation that transformed this inertia tensor to put it in a new form that's n by n. But it's the same thing. It's the same thing in the end. This was the inertia tensor that includes makes the kinetic energy. And in the end, the M here is just its reduced form. So these are what I'm trying to say here is that these are the same expression. So this one and this one, they're the same nature. This is what's inertia. This is also inertia. This is why it's called the mass matrix. The same also here. You see here we had some Coriolis term, some gyroscopic term, and this is why in the literature this is called the Coriolis and gyroscopic matrix, because again it comes from all of the expressions that we had on top, and of course the cross coupling between all of these bodies together. This is, you don't write this on paper. Okay, I just wanted to show you once in your life. This is what goes into the computer. So when you build a robot with the URDF file and it transforms for you and it builds a simulation, a tool in the simulation, for example, using Gazebo or MATLAB and so on, it does all of this in the background. Okay? But it's very simple if you have the correct tools to actually go back and forth between. Okay, you're going to be calculating this at least once also in your lifetime in the course, inshallah, in an assignment. Okay, with some code, and gonna have fun. Okay, but not for now. Okay, let's just end. And if you have any questions, I can take.